Hello, and welcome to Chapter 10 of the Joy of Abstraction Book Club. Thank you very much for being here. Thank you to the Topos Institute for hosting, and thank you for your questions. There's way more questions than I was expecting on Chapter 10, and so I'm really glad that there's a lot of interest, because I thought, oh no, it's a really short chapter, maybe no one will have any questions. Silly me. Anyway, I've had a pretty long day today doing crit panels at SAIC, and so I am not sure how this will go, whether I've got the energy, but let's see. The first question is, could arrows always be thought of as embeddings? So in case you don't know what an embedding is, an embedding is, well, it's like embedding something inside something else. And so it's a bit like a subset, or where you take a space and you kind of stick it into something else, but you don't collapse it in any way, you really just put it in. And that is a very special kind of mapping. And so because it's very special, I would say, no, we can't always think of arrows as embeddings, because there are way more kinds of arrows than that. There are arrows that break things apart, there are arrows that loop things up on each other, and there are arrows that are nothing like maps whatsoever. So I would say no. The next question is, if statements have a category structure, can mathematical proofs themselves be written as categories? I'm not sure what this means. I think that statements and proofs can be made into a category where the statements are the objects and a proof of one statement from another is a morphism. I don't know that statements themselves have a category structure. I suppose you could make a category from a statement where somehow all the objects are the words or something, but I'm not sure what that would do. Okay, next question. Does category theory ever run into trouble when it deals with infinite sets? I'm trying to work out what you're thinking of, because typically infinite sets aren't really very problematic. The ones that are problematic are the ones that are too big to be sets. And so I can't think of any problems that would come from just thinking about infinite sets. We humans run into trouble when we think about infinite sets if we don't do it rigorously. If we try and do it intuitively, we get into trouble. But if we do it rigorously, I don't think it's a problem. Next question. Can generalizations themselves be thought of as posets? Not quite sure what that means either. A poset is a set of things with an ordering on it. So when you say generalizations, do you mean can the generalizations themselves, so the objects are the generalizations, and then you want to put some kind of ordering on the generalizations? Maybe to say which ones are more dramatic generalizations than others? Maybe that's a possibility. Would you mind telling us what's the most surprising example of a poset that you know, something that we wouldn't normally recognize as a poset? Well, of course, surprise is relative, right? Different people are surprised by different things, and once you're comfortable with something, it's not very surprising anymore. So one of the things that I've talked about the most in public is the poset of privilege, which is really just an example of the poset of the power set of a set. So the power set of a set is all its subsets ordered by inclusion. And the poset of privilege is just a poset of the power set of some number of, a set of some number of objects. So you can take any 3-element set and take its poset of subsets, and you will always get a cube shape. And those 3 things could be anything. And so I just happen to say they could be privileges, and then you get a poset of privilege. That does seem to be surprising. I think that there are many posets around us. I've got to a point where I expect them, so I suppose I don't find them surprising anymore. And I think that what is more illuminating for me is looking at when we're thinking about maps between posets that aren't order preserving. I think that can be surprising. For example, a student actually pointed this out to me about triage being a case where you specifically don't want ordering to be preserved. So I think that's what I would say about that. Is it fair to say that large categories are the main point of category theory and that small categories are like extra bonuses that we get for free? I'm not sure I'm comfortable declaring what the main point of category theory is. First of all, because I don't feel the need to put everything in competition with each other and make one thing the main thing. Second of all, because the point of category theory is different for everybody. And I don't think I'm comfortable declaring overall on behalf of everybody what the main point is. I think that it is arguable that large categories are the main point, but I might also say that category theory isn't driven by examples, and so it's not the large categories that are the point because it's not driven by examples. Next question. I noticed that we can represent a group as a category, but it seems impossible to represent a ring or a field as a category. I wonder why you think it's impossible to represent a ring as a category. First of all, a ring is just a group with some extra properties. So it's definitely, if a group can be represented as a category, then a ring can also be represented as a category. If you mean that it doesn't have a neat definition as a category such that, that may be true, and that's because it's got two operations, addition and multiplication. But we just need a little slightly more nuanced form of category theory. So if we, this is more advanced, but you asked, so I'll answer it. But there's a concept of internal category. And what we've done so far is category theory with sets. We've got sets of objects and we've got sets of morphisms. If we do category theory internally, then we can do it internal to some other category. And if we look at internal category theory inside the category of abelian groups, then a ring is an internal monoid in abelian groups. So yes, it can be expressed. If something can't be expressed in category theory, I wouldn't necessarily call that, so then the next part of the question is this a deficiency of category theory? So just because something can't be expressed in category theory, I wouldn't call that a deficiency in category theory. I might also call it a deficiency of that thing. But on the whole, it's just a different thing. Maybe it's just giving us a sign that they're looking at things from a different point of view. So if I say that my vacuum cleaner can't make tea, I don't think that's a deficiency of the vacuum cleaner because it was never trying to make tea. Similarly, my teapot can't vacuum clean, but that's not a deficiency of the teapot either. Yeah, I think that's what I would say about that. Okay, next question. Does ordered set mean toset, or is it a general term for toset and poset? Great question. Do you know, I have no idea. And I suspect that I use it generally as a general term for toset and poset because that's what this chapter was called. It was called ordered sets. But in a specific situation, I would want to make it clear which one I'm talking about because otherwise it's a bit too ambiguous. Can I say that loop is a special case of parallel? So I think this is about the examples of things that aren't tosets. And I did say that the one with loops is technically the same as the one with parallel things because it's just that the parallel arrows happen to have the same endpoint. So yes, I would say that that is a special case of parallel. Someone else says, page 120, could you possibly explain in more detail why the two composite arrows from 2 to 6 to 30 and 2 to 10 to 30 are the same? So what I said in that part is that the arrows in the category of factors are simply the assertion that A is a factor of B. And so what this is really coming down to is the definition of arrow. So if A is a factor of B, well, perhaps I'll open the whiteboard now. In the category of factors, there is an arrow from A to B, which just means that A divides B, right? And so the reason that composition works is that if you have A arrows B and B arrows C, this means A divides B and B divides C, right? But this we can deduce that A divides C. That's a fact about divisibility. So we have an arrow, whoops, A to C, because arrows are the assertion A divides C. And so by definition, this is the composite. So that's how we've defined our category structure. And this is true no matter what the B in the middle is. And so that's why 2 to 6 to 30 composes to the unique, there's a unique arrow from 2 to 30. And 2 to 10 to 30 also composes to the unique arrow from 2 to 30. So those two arrows in this category have to be the same because there is only one arrow from 2 to 30. It's just the arrow declaring that 2 divides 30. So if our arrows were proofs rather than just assertions, then those two wouldn't be the same, because the proof via 6 is different from the proof via 10, right? The proof that 2 divides 30 via 6 is that 2 divides 6, which means that 6 is 2k, and 6 divides 30, which means that 30 is 6m, and therefore 30 equals 6 times 2 times k. So this is 12k, right? This proof that 2 divides 30 says 2 divides 10, which means that 10 equals 2n, and 10 divides 30, which means that 30 equals 10l. So 30 equals 10 times L. So it's 10 is 2 times n, so it's 2 times n times L. I did this completely wrong. So this is wrong. What I'm supposed to be doing is substituting the 6 into there. So 30 equals 2km, right? And here 30 equals 2nl. And so look at these two proofs. These two proofs, they come out looking the same, but the two proofs are different along the way because one of them goes via 6 and the other one goes via 10. So if these were proofs rather than assertions, then we could have multiple arrows from 2 to 30, but they're not proofs, they're assertions. And so we can only have one arrow from 2 to 30. And so these composites are both the same. Okay. And so finally, we have the question, when you say the diagram of quadrilaterals and their generalizations was another poset, which ones exactly? So I was referring to, this is on page 123. And what it says is, look back at chapter 5. Can you see any other posets that we looked at in that chapter? So in chapter 5, we had family trees. Those are probably not posets. Symmetries, those are probably not posets. We had arithmetic, that's probably not a poset. Modular arithmetic is not a poset. We had the quadrilaterals and generalizations. That's a poset. The lattices of factors we've already looked at in this chapter. So that's a poset, and that's all the examples we had in this category, in that chapter. This question goes on to say, does this mean not any of what I can only call the smiling or toothy arithmetic diagrams because they have too many arrows? So I think you mean these, do you mean these ones? They're kind of smiley. For future reference, a page reference would be helpful. Those arithmetic diagrams do indeed have too many arrows to be a poset. And so, wait, let me think about it for a second. Are we just doing arithmetic? Okay, pause while I think about it, because I only just realized that's what you're referring to. Interesting. I think that maybe the arithmetic ones are posets, because there is only at most one arrow from one to any other, because we're only doing addition here. So from 1 to 2, there can only be one possible arrow, because if we're only doing it by addition, all we can do is add 1. The modular arithmetic ones should not be a poset, because there are different ways to get from 0 to 1, because you could add 1, but you could also add 5. If adding 5 is not an object in your category, so I haven't really defined this category very clearly. If adding, supposing you've only got adding 1, adding 2, adding 3, and adding 0, then, oh, I think I need to think about this again. Okay, few. Modular arithmetic is not a poset, and the reason is that a poset has to have, given any objects A and B, at least one arrow between them, not necessarily from A to B, but between A and B. And in the modular arithmetic category, 0 and 1 have 2 arrows between them, because you can add 1, or you can add 1 to get from 0 to 1, but you can also add 3 to get from 1 to 0. So let me just share that little screen again. Okay, so in the modular arithmetic category, we have 0 and 1. We have an arrow going that way, which is +1, but we have an arrow going this way, which is +3. This is in modular arithmetic. So that's not a poset. Okay, very good. I think that's all the questions. So some praise. I wish more instructors did this. I was trying to stop the screen share. Praise. I wish more instructors did this. Thank you, Professor Cheng. Well, thank you all very much. I'm going to actually make the chapter 11 video immediately. So see you next time, which for me is very soon. Bye.